Hey, it's Dr. J. We're back with some more calculus today, more on the quotient rule, and then we're going to learn a new business application called marginal averages. So let's get right into it. So recall the quotient rule. The derivative of a quotient. Now I'm going to use the shorthand notation just because it takes up less space. This is really f of x over g of x. We call that the shorthand. It just gets redundant to write f of x, g of x, f of x, g of x over and over again. So whenever it's clear that the variable is x, which is like 90% of the time, I will omit the x, just say f over g. So remember, the quotient rule is f prime g minus g prime f over g squared. That's the quotient rule. I should probably remind you of the product rule, because we're going to be using that today. I know it's not in the title, but so fg, or in other words, f times g, is f prime g plus g prime f. It's basically the numerator of the quotient rule, but with a plus sign, and then there's no denominator in the product rule. So just a quick refresher of the two rules we learned in the last video. Now remember, the letters may change. We won't always use F and G. The next best thing is, say, a U and a V. So let's do an example of both rules combined. So 2x ln of x over 9x plus 6. So we're going to use the quotient rule. The numerator is f, and the denominator is g. And so dy dx is the derivative of this. I could write that out, d dx, like I did here. I'm just going to say it, derivative with respect to x. So that's going to be the derivative of 2x ln of x times 9x plus 6. So this is f prime, and this is g. I'll just keep this handy. It's a tiny little f prime there. F prime. There we go. Minus, all right, g prime. Now, g prime is very easy. I'm just going to go ahead and do it. It's 9. Yeah, so that's g prime. Right. Notice I haven't done f prime yet. I've just indicated that I'm about to. So I'm waiting on the f prime right now. I just went ahead and did g prime because g is such a simple linear function. It's a line, 9x plus 6. It doesn't have an exponent larger than 1, so that's just g prime. Times f. So f is 2x ln of x. So that's f. And then this is going to be all over g squared. Okay. But now, because f prime is a product, Yeah, so we're going to need the product rule. We have the derivative of 2x ln of x is going to be 2 times ln of x plus 2x times 1 over x. So that's the derivative, let's say u and v. Right? I'm calling 2x, I'm calling u, and ln of x, I'm calling v. And so then this is u prime. Here, let me use the highlighting color. This is u prime times v plus u times v prime. Right? And again, with the product rule, the order doesn't matter. Sometimes I say v prime u, and sometimes I say u v prime. When you're multiplying and adding, the order is not as important. However, when you're subtracting, the order is very important. So I have to make sure I keep this subtraction in the correct order. So I've got 9 times 2x ln of x. And I've already done that. And then all over 9x plus 6 squared. I'm not going to completely simplify. I'm just going to sort of lightly simplify. So just 2 little things I'm going to do. I'm going to cancel these x's. And I'm going to distribute the 9 here. 9 times 2x. Just to make the final answer look a little... oh, shoot, I lost something. Oops. I almost lost that there. Look at that. That goes right here. So let's see if we can squeeze that sucker in. There we go. Good thing I caught that when I did. All right. So, oops, I almost lost a piece. I was expanding the derivative of the 2x ln of x, and I almost forgot my 9x plus 6 here. But I caught it, so here we go. So we've got 2x ln of x plus 2. Yeah, because I can cancel these x's here. I'm not going to distribute the 9x plus 6. It would just make a big mess. I am going to distribute the negative 9 here and just make that negative 18x ln of x. That's just a, monomial. It's just one term, so that's easy to multiply. Over here, if I wanted to multiply the 9x plus 6, it would make a big mess. So just leave that unsimplified or undistributed, and you can call that your answer. In this lecture, I'm not going to be simplifying many of the more sort of messy examples because the simplifying really doesn't make it any easier. So that is your final answer. I played around with this for several minutes before, deciding on how I wanted to leave the final answer, and it really doesn't get much better. You could try. I mean, there's some simplifying that you could do, but it really is just not worth it. So unsimplified is okay with me. Unsimplified. All right. Really, that was just sort of a reminder of the 2 rules and how they kind of incorporate together sometimes. Let's do another example, an even messier example. And I'll try to get it all on one board if I can. If I plan out my example nicely, I can do it. So the next example, 2. Another one of these functions that is a combination of a product and a quotient. Oh, f of x. So we have again we could plan this out. You have a combination of 3 functions here. The function is called f, so it gets messy or somewhat misleading to call the component parts f and g and such. So I'm going to go with u. We'll call this one u. Call this one v. And then we'll call this one UVW. Okay. So this is sort of my plan. You don't really have to plan it out if you don't want. You can just kind of jump in and see what happens. But my plan is I'm going to take the derivative of the top. So that's going to be u prime v plus v prime u. So the top is a product, yeah, times the bottom, w, minus the derivative of the bottom, w prime, times the top, which is uv. Or I could do, like this, uv, like that. Oh, all over the denominator squared, which I would probably use parentheses on the denominator as well. So that's my plan. Let's see how it goes. So f prime of x, I'll give myself plenty of room. All right, so u prime, that's going to be 6e to the x. Technically, it's 6e to the x plus 0. Yeah, the derivative of 7 is 0. Times v, 2x to the 7th plus 8x. Plus v prime, so that'll be 14x to the 6th plus 8. Right, that's the derivative of v, times u, 6e to the x plus 7, minus w prime. Oh. Almost screwed this up. So this is, glad I have my plan here. This is u prime v plus v prime u. And then I got a w here, so I need an extra set of parentheses. I'm going to use brackets. W is 3x squared plus 9. Still didn't give myself enough space. Here, let's slide all this over. I don't have to do it over again. I'm just going to slide over. If I do this right, I can just do it once and be done. 14x to the 6th plus 8. 6e to the x plus 7. Okay. So now I've got, this is u prime v plus v prime u times w, the bottom, 3x squared plus 9, minus All right, w prime, so that's 6x, derivative of the denominator, times uv, which is the top, just copied exactly the way it is, 6e to the x plus 7, and 2x to the 7th plus 8x. All over the denominator squared. And that's it. That's your final answer. You do not have to simplify it. Better if you don't. Okay, if you try to start canceling stuff or combining stuff, I mean, it might be right, it might get better, but it probably will just get worse. In chapter 3, we might want to actually analyze this a little further, and how it relates to the function and to the behavior and the graph of the function. So there might be some more techniques coming down the road, but for this chapter, when you have these really messy ones, you can just leave it unsimplified. Sometimes I'm very expressive about that. I say, do not simplify. Other times I'll say, simplify as much as you can, or simplify if you choose. Depends how complicated the problem is. For this one, I'd probably put in capital letters, don't touch it. Put it down before you break it. Okay. So it's really just an exercise in following the steps. It's not meant to give you a very clean or neat answer. Let's do one that's kind of the reverse of this, where there is 2 factors in the denominator. Let's see what the plan for that would look like. So something like this. All right. So again, you want to make a plan or not. If you don't feel like you need a plan, you can just dive right in. I'm glad I made a plan last time. It kind of saved me. So this time I've got 2 factors in the bottom. All right. Now again, I can label them any way I like. I can go A, B, C if I like. U, V, W. I wouldn't do F, G, H because the function's already called F, and that can get confusing. But you know, you can do whatever you like. If you're not going to be confused by it, you can. I'm just going to try different letters to show you the technique. So we got the derivative of the top, so it's going to be A prime, times the bottom, so it's going to be B and C, minus, straight to the quotient rule. Yeah. Now the derivative of the bottom, so that's going to be a product rule. B prime C plus C prime B times the top all over the bottom squared. Now it's going to be BC squared, but since they're 2 factors with parentheses, I'm going to put B squared, C squared. I will put parentheses around them like this. All right, that's my plan. And if I do this right, I can get it all done in one clean line. One big messy line here. See if I can get it all the way before I reach the end of the board. Okay, so A prime. A prime is pretty easy. That's just 4. And then BC. So 5x squared plus 2x, 8x squared plus 7. So that's A prime BC minus B prime. It's going to be 10x plus 2. That's b prime. 10x plus 2. Times c, 8x squared plus 7. Plus c prime, 16x. Times b, 5x squared plus 2x. Times a. Shoot, I don't have room for a. Let's see if I can go a little smaller here. 10x plus 2, 8x squared plus 7 plus 16x, 5x squared plus 2x. There we go. So that's this bracket here, b prime c plus c prime b times a, 4x plus 3, all over b squared c squared, so 5x squared plus 2x squared, and 8x squared plus 7 squared. There you go. All right, so again, do not simplify. Or I should maybe say simplify at your own risk. If you can simplify this and get it clean, it's a nice, mental exercise, academic exercise. I'll leave it to you. If you're just trying to get your points and just want to move on to the next problem, especially on the test, the upcoming chapter test, don't waste a bunch of time. Just put together the pieces and move on to the next problem. All right, I got one more of these, and then we're going to get into the get back to business math. So another one of these. Today's business math topic is average and marginal average. So there's two types of averages that we're going to be calculating. And I'll actually do a business example in a minute, but for this example, it's just an abstract function with an x in the denominator. So you'll see this in some of the business applications. When you take a function and you divide it by x, we call that the average function. All right. Now in this, I'm just calling it f of x, but just going to kind of open up the door to why it's included in the quotient rule, because we're dividing by x, and that's a quotient, and that'll lead us into the next topic. So let's just go ahead and find the derivative. This one actually is not too bad. It does have a product rule and a quotient rule. I'm going to try to do it without a plan. Right? I'm just going to try to dive right in and see what happens. So I got a product rule. All right, so let's do that first. Derivative of the top is 9. And 2 times the square root of x cubed. I probably would rewrite this as x to the 3/2, or at least mentally rewrite it that way. And then when you take the derivative, it's going to be 3/2 x to the 1/2. Remember, you're subtracting 1. So when you subtract 1 from 3/2, the power will become 1/2. All right, so I'm going to do that next. So it's going to be that plus, now the derivative of that, of the second piece here, which is going to be 2 times 3/2 x to the 1/2. I can use parentheses if I want as well. And then times 9x plus 4. So that's just the derivative of the top, right? Then I got to multiply that by the bottom. Minus the derivative of the bottom, which is 1, times the entire top. I'm just going to write copy. 9x plus 4. It's getting kind of tight. I think I will rewrite this one time. All over x squared, the denominator squared. So let's see if I can clean up my answer just a tad. Just to, how I would present it for the final answer. So I would do 9 times 2 square root of x cubed minus 1 plus 3. See, these 2's will cancel. Times the square root of x. I would put the 1/2 back as the square root of x. Times 9x plus 4. Bracket, square bracket, then x. Then minus, I wouldn't even write the 1. I mean, you could write it if you want, but it's there, whether you write it or not. And then 9x plus 4. And then 2 times the square root of x cubed minus 1. All over x squared. And that's as much as I would do in this chapter, especially in this section where we're just exercising the rule. Perhaps in the future, I might distribute the x here, get rid of some of the non-essential parentheses. We might try to factor this out. We might even try to solve for x at some point, but not today. All right. So that's going to do it for the introduction to the introduction to the to the video where we're going to apply the quotient rule to some of the business math problems. So next, let's get back to business and see how that works. So next, some business applications. So given a cost function, if you divide by x, this is called the average cost function. All right. So I'm going to give you three new types of functions. We'll have average cost, average revenue, average profit. Okay. And what we do is we give them new names. We put a little hat on top of it. Some people call it a hat, some people call it a bar. I guess I'll use the term bar. So I'll say R bar, C bar. It means average. We sort of have debates in mathematical circles about whether it's a hat or not. Some folks insist for it to be a hat, it has to kind of have a little point at the top. So since that doesn't have a little point, we don't call it a hat, we call it a bar. It's too flat to be a hat, but I mean, I call it a flat hat. I don't know. I'm going to use the agreed upon terminology, which is that's a bar. So we call that C bar, R bar, and P bar. All right. And again, it's equal to this. I really should have written it in a better spot. So this is C bar, this is R bar, and this is P bar. Called the average cost, average revenue, and average profit. Notice there's no calculus yet. We got to take a derivative for it to be calculus. But not every calculus problem involves calculus. So let's do an example that does not involve calculus. Example 5. So this is a good old algebra problem hidden into a calculus problem. The cost for a family farm to produce X pounds of peaches is given by the function 3x plus 105. Obviously in dollars. I should probably mention that, but I think it's clear. Unless otherwise specified, we should assume everything is in dollars. There might be some mega math that we do later where we're talking in hundreds of dollars or thousands or millions or some larger quantity. It's typically in the United States dollars, though, in this particular course. And the price demand function, remember, price demand is not the same as profit. It's the lowercase p. All right. So I have a cost function and I have a price demand function. Find the average cost, average revenue, and average profit when 200 pounds of peaches are grown and sold. or produced. Interesting. When you go to the grocery store, we call it the produce section. Yeah, I think that's funny. It's produce. It's been produced, yeah, or it's been grown. We don't call it the growing section, well, the produce section. A little fun fact on where that term comes from. All right. I've probably never even thought about it that way, did you? I know I never did. All right. Cost is pretty easy because we have the function already. So it's going to be 3x plus 105 over x, 200 pounds of peaches. We're just going to plug in 200 for x and stick it into our calculator. There's no calculus here. This is just algebra and arithmetic. So I got 600 plus 105 over 200, 705 over 200. We'll round to the nearest cent because it's money, 3.53. So this is dollars per pound. All right. So think about what that means. You have this cost function. Right? It's costing you $3 to grow each pound of peaches, but there's $105 in fixed costs. Yeah, which is pretty low. In the grand scheme of things. I'm assuming that this model, has already been developed. We didn't go through any process to develop the model. We trust the model. So whatever that $105 covers, it covers some fixed costs that you have to incur even if you don't grow anything, right? So even if you had no peaches at all, you're still stuck with $105 in costs. Right? I always think of it as just rent. Got to pay the bills, right? Now, when you start growing the peaches, it's $3 per pound. That's probably for water and whatever, labor, things like that it costs you to grow the peaches, right? But on average, so this all averages out when you divide by X, the number of peaches, the number of pounds of peaches, 200 pounds of peaches. If I grow 200 pounds of peaches, on average, it's costing me $3.53 for each pound. Right? That's an important number to know, right? Because if you were selling peaches, you wouldn't want to sell the peaches for less than this average, right? Because then you'd be losing money on average, right? Now, if you're just trying to get rid of them so they don't go bad, maybe you'll take a loss. I don't know. I'm not a farmer. I'm a farmer of mines, not of peaches. All right, let's try revenue. So remember, revenue is P of X times X. And again, this is lowercase p. You got to be really careful with the P's. Sometimes I'll write them clearly different than a capital P so I don't screw them up. All right, put a little flair in it or something. This is a Greek letter. It's not a P though. It's a rho. Which is kind of cool because it's like an R, rho. It's a Greek R. I'm getting off topic now, but a Greek letter P is actually pi. It's the symbol that we use for pi. So the Greek letter R looks like an English P. All right. So R of X is P of X times X. You just multiply this by X. I'm not showing the math. I've done it before. This is calculus. When you multiply the price demand by X, you just get the same function with an additional X. So it becomes X squared and it becomes 5X. Okay. And then now to do the average, my head's not in the way. I'm putting the bar or the flat hat. I'm going to divide all of this by X. Interesting what happens it just goes right back to being the price demand function. Oh, interesting. Oh, that's worth noting. Yeah. So in this particular example, when you find the average of the revenue, right? Because the revenue is price demand times X, revenue bar is price demand times X divided by X, right? The bar here. I don't know if that's clear here. It's getting lost in the shuffle there. Yeah. The X's cancel, and you'll notice that the revenue average with the bar on top is just the same as the price demand. So that means R bar of 200 is the same as just taking the price demand function and plugging in 200. I wouldn't memorize that as like a permanent fact. It's a sort of a fact in this instance. So because this revenue function was such a simple function, right? It wasn't very exotic. It didn't have any logarithms or exponentials or anything like what else? Square roots, anything like that. It's a very simple function. Then we got this as a very simple revenue. This is the average revenue for selling 200 pounds of peaches. So that'll be, I should be able to do that in my head, but I'm not gonna embarrass myself. 2,000 times 0.005. Oh, now I'm really embarrassed. Negative 5 is positive 4. All right, so it's costing us $3.53 per pound to grow the peaches. We're selling them on average. Again, that's average revenue for $4 per pound. And so we could figure out the average profit. Before I write anything down, you guys are educated college students, very well versed in common sense, I hope. If it costs you $3.53 per pound to grow something, right? This isn't calculus anymore. This is just arithmetic, and you're selling it for $4 a pound, just using your intuition. The profit margin on average I'm just going to write it out in words. Intuition, the average profit is 47 cents per pound. I haven't even written anything down yet. And it's just, as soon as you see the cost and the revenue, you can already start predicting the profit. Now, they're not always going to be this arithmetic and simple. All right. So let's go ahead and do the math, because I want you to be intuitive, and sometimes your intuition is correct. In this case, it's definitely correct. But I just want to show you how to do the algebra in case your intuition fails you. Yeah. Or if you're just kind of plowing through the math and not really thinking about your intuition. I mean, you have other things on your mind. I know sometimes math is a nice way to escape and not really think about a lot of things. And sometimes you get, deep into it, and I know I do, and you don't even think, oh, shoot, this is just, dollars and cents, and just kind of get the basic idea. We sometimes call that overthinking. So remember, profit is revenue minus cost. So our revenue was negative 0.005 x squared plus 5x. That was our revenue. Our cost was 3x plus 105. Yeah, 3x plus 105. I always put extra parentheses around the cost when I'm doing this because the negative is going to change the signs. That's going to become negative 3x. That's going to become negative 105. So this is not the average yet. This is just the profit function. So this is the function that tells me how much profit I make. If I put the hat on it or the bar, then I divide this whole thing by x. Okay. And I should get 47 cents per pound because I already know the average cost and the average revenue. But let's just go ahead and do it. So P hat 200 is negative 0.005 times 200 squared plus 2 times 200 minus 105 all over 200. You could simplify this first. I decided not to because you're going to get the same result anyway. Maybe in my next example, I'll show some techniques for cleaning this up a little bit before we get into it. We have to get back to doing calculus. So I just want to wrap this one up. And to simplify it would take me longer than just to finish the problem. So this is going to be, I'm just going to do this all on the calculator here. So I've got 200 squared, which is 40,000 times 0.005 negative. So that's going to be negative 200 plus 400 minus 105 over 200. You see, it would have taken me longer to simplify it than it would just to put it into the calculator and see what I get. So negative 200 plus 400 minus 105 is 95 divided by 200, and I get 0.475. That rounds to 48 cents, or we're going to say $0.48 per pound. The reason why it's off is because of rounding. There is a rounding error. If you recall, the revenue didn't need to be rounded. It was $4 per pound, but the cost, we rounded it. Right? We rounded it by a penny. And so by rounding it by 1 penny, it threw off the average profit as well. This is the correct answer that I want, is 48. My intuition was pretty close, but not exactly 48 cents. And again, it's the rounding error. Yeah, we had 0.5s on both sides of it, and they both got rounded up, and so you have that extra penny. Right? We could argue whether that extra penny actually exists, right? Because in real life, do you always round up? I know for myself, if I don't have a whole penny, I round, even if it's 0.9. If it's not a whole, it's gone, right? If it's less than a penny, it doesn't even exist as far as I'm concerned. But that's a whole nother debate. And maybe later we'll talk about gas prices, because not today. We don't have time to talk about gas today, but it's kind of interesting how gas prices, you can actually have less than a penny. You might not have noticed that, or you may have noticed it when you're filling your tank. I'm not going to get there. I just want to tell you today's answer for average profit is 48 cents per pound. I'm not going to use the word cents. I'm going to use dollars because it's $0.48, which means 48 cents. But I don't want to get all into that today because it's too complicated for the computer if you write 48 cents. So just tell it it's $0.48. All right. So let's get back to calculus. That took me way too long. What does this have to do with calculus? Well, back to calculus. If you have the derivative, if you take the derivative of any of these functions, this is called the marginal average. So that would be marginal average cost. This would be marginal average revenue. And this would be marginal average profit. All right. So we start with the average, then you take the derivative. Yeah. Derivatives, I guess. There's three of them. Then you get what are called the margins or the marginal averages. Let's use exactly the same problem that we just did, but let's take the derivatives. So example 6. Recall in example 5, C of x was 5x plus, no, not 5x, was it? It was 3x. 3x. If you're going to recall, you recall correctly. 3x plus 105. R of x was negative 0.005 x squared plus 5x. And P of x was negative 0.005 x squared plus 2x minus 105. So those were the three functions that we had. Find the marginal averages when 200 pounds of peaches are produced and sold. Okay, so start with C bar. We'll do one at a time. Start with cost. So that's going to be 3x plus 105 over x. Wait now to plug in the 200. If you plug in the 200 now, you're just going to get the same answer we got in the last example. So wait to plug it in. All right. Take the derivative. C bar prime, which is why this is in this section. This is a quotient. Yeah, so we have a quotient rule. So derivative of the top. It's a pretty easy quotient rule, but it's still a quotient rule. Derivative of the top is 3 times the bottom minus the derivative of the bottom, 1 times the top. All over the bottom squared. Much easier than the problems I was doing at the beginning. I kind of started strong with some very intense algebra. When we get to the business math, the algebra lightens up, at least for a minute. It'll get tough again later. So let's enjoy this while it lasts. So this is going to be 3x minus 3x minus 105. Remember, this negative distributes, like multiplying by negative 1. It is multiplying by negative 1 over x squared. Cancel the 3x's because one of them's negative, one of them's positive, and you're going to get negative 105 over x squared. Now you can plug in the 200. If you plug it in too soon, it won't be right. So we got negative 105 over 4,000, 40,000. Yeah, so this is less than a penny. It's because it's too many pounds. Too many pounds. Which essentially means, and think about what this means. This means that the marginal average, right? How much it's increasing or decreasing, yeah? It's decreasing by less than a penny per pound, which is pretty flat. That essentially means that your cost, I mean, I'm trying to explain not only how to get the right answer, but intuitively, practically what this means. All right. It means that it's decreasing average cost by less than 1 cent per pound. That's the interpretation of what that means. In your homework, you would round to the nearest cent. So this would be 0. The answer would actually be 0. I think I just kind of dove in a little too hard on this one, a little too deep. 200 pounds was too many peaches. I was trying to sell too many pounds of peaches. If this number is less than 200 pounds, then you will get a number that is not 0, all right? If this does happen to you, just type the whole thing. You don't have to round it. I will mention, though, if this was a 5, all right, if that 2 was a 5, then you would round it to 1 cent or negative 1 cent, all right, which is, I think, what will happen when you get this problem. It's going to either be 1 cent or 2 cents, or it won't be this small. But I'm not stopping the video now. I tried to grow too many peaches, and I got 200 pounds isn't that many, but anyway, that's it for cost. Let's move on to revenue. Let's sell these darn peaches, okay? And I'll keep it at 200 pounds. Or maybe I'll change it. Let's do 50 pounds. I'm going to change it. All right, you're not allowed to do that. You have to do whatever number is in the problem, but let's do 50 pounds. So this would be average marginal cost of 50 pounds. Now this is just it's not explaining what I want it to explain. You don't have to do all the work over again. Just plug in 50. I want to model what is more likely to happen in your experience. It still might be less than a penny. So it's going to be 105 divided by 2,500. Oh, no, that's fine. So that's, oh, it's actually positive. No, it's negative. Negative divided by a positive is negative 0.042. So this is what would happen in your homework or test or something. This would be decreasing at this rate, dollars per pound. And again, we say dollars, but that really means -4 cents. So I hope that is a better example of what you might actually see in your homework. So now that I've switched it to 50 pounds, let's just do the rest of them at 50 pounds. So R hat negative 0.005 x squared plus 5x over x, and then R hat prime. Now, in this example, it's so much easier to simplify first. Remember, we already knew that R hat, I'm not going to take the derivative yet. I'm going to simplify first, which is, I hope you're catching on. Sometimes I simplify first and then I take the derivative. Other times I just take the derivative and I don't bother trying to simplify it. It really depends. Now, I have a lot of experience, so, I kind of know when it's going to go good and go bad, but I'm not always right. Sometimes I think something's going to go well and it goes bad. In this particular example, because all of the terms have x's, it's easier to simplify first and then take the derivative. In the last example, it really didn't matter. Now remember, this is a linear function, so the derivative of a linear function that's it. You're done. Yeah. There is no x. You are going to approximate this. So this will be 1 cent, -1 cent. All right. So average revenue is decreasing at a rate of 1 cent per pound. LB for pound. Average cost is decreasing at 4 cents per pound. And again, I say cents per pound, but when I type it, it's dollars per pound because it's written as a decimal. So the revenue is actually going down. As I sell more, or when I'm selling 50 pounds, it's going down. And let's get to profit. So that's revenue. Notice I never had to plug in the 50 here. Yeah, because when I took the average, I got a linear, and then I took its derivative and I got a constant. And when you get a constant, you're done. Yeah, that's it. Profit now. So here's our profit function. So our average profit function is -0.005 x squared plus 2x minus 105 over x. All right, so I'm still going to do 50 pounds. I'm going to wait to plug in the 50, though. If you plug it in now, it'll be wrong. So now take the derivative. Now, I don't know if it's easier to simplify it now or simplify it later. I just showed you both techniques. I'm just going to go with leave it alone. I think it's nice to practice the rules. So the derivative of the top, that's going to be 2 times -0.05, which is -0.01 x plus 2. So that's the derivative of the top times the bottom. minus the top, or the derivative of the bottom, 1 times the top. It's very messy, all over the denominator squared. All right, so that's going to be negative 0.01 x squared plus 2x plus 0.005 x squared minus 2x plus 105 all over x squared. Here's the fun part. Cancel the 2x's. Combine these guys. Want to use a calculator, you can. 0.005 minus 0.01. Oh, look what it does. When you combine this one and this one, I should have seen that coming. Again, I've done this a million times. I just didn't see the light, you know. When you combine those, it goes right back to being what it originally was. Tells me I probably should have just simplified this first. Plus 105 over x squared. So now we're going to plug in 200. No, not 200. That's too many. That was example 5. I'm growing less peaches in example 6. 50 pounds of peaches. So P average prime, or the marginal average, I don't want to do 200 pounds. 50 pounds, negative 0.005, 50 pounds squared, plus 105 over 50 pounds squared. All right. You could try to cancel the x squareds. I didn't do that because I'm afraid if I just cross them off, I'm going to get the wrong answer, and I will. But if you do it correctly, you could pull it off. All right. I don't want to show you how to, do something incorrectly, but then manage to get the right answer because, of magic or something. So I'm just going to show you the step-by-step method. So you got 50 squared, that's the 2,500, times 0.005, and then negative. So it's negative 12.5 plus 105 over 2,500. So 92.5 over 2,500. And so, those are both positive. So that's positive 0.037, that's actually exactly 0.037, but then it's approximately 4 cents, or $0.004 per pound. So when you are growing 50 pounds of peaches, your profit is increasing at that moment. Like when you grow the 50th pound and sell the 50th pound, you're growing it and selling it. I mean, in your mind, you could think, you grow it and then you put it out on the farmer's market and sell the whole 50-pound bushel or whatever it is. I don't know. I'm not a farmer. But you have to sell all the peaches, right? You sell all 50 pounds, then your profit, on average, again, it's an average, is on average 4 cents per pound. Not a good way to make a living, right? I mean, I guess you have to really love it, right? You're only making 4 cents on every pound of peaches. Okay. But I mean, if you sell millions of pounds or hundreds of thousands of pounds, maybe you could make a good living. But oftentimes business is thought of as living within the margins, or living on the margins. It's marginal profit. You're just making this little bit off of each pound, right? Now, why is this useful? Why would a business person want to do this? Well, it's all about predicting, right? We want to be able to predict what's going to happen, right? And then making correct decisions, or maybe the right decision, or sometimes even the wrong decision, but you're making that decision based on information, based on a pattern, based on a model, right? Not all models are perfect. It doesn't take into consideration unforeseen events of nature or of the economy, but we can still, move forward and try to make things work. Okay. Let me show you a couple more examples. Example 7. Let's just do cost. I don't know what these are. I just want to show you some more interesting models. So this is the cost to produce X units of some product. All right, again, widget, gidget, gadget, gizmo. Doesn't really matter. But this is an interesting cost model. All right, it's not linear. So this type of model is kind of like this, where as you go along, right, the cost is getting a little cheaper and a little cheaper and a little cheaper. And then to produce 1 unit, right, if you plugged in 1 for X, I'm not going to ask you to graph this. I'm going to erase this in a second. But before I do the problem, I kind of want you to see why it's different. In the last example, the cost model was a straight line, right? Well, this one's not a straight line. The cost to produce 1 unit is $635, right? And if you don't believe me, plug in 1, take the ln, you're going to get 0. I hope you believe me. 0 times 27 is 0, and then plus 635. You cannot produce 0 units, right? So it's just starting with 1 unit. So X has to be greater than 1. Okay. So then as you produce more units, the cost gets cheaper, right? A linear model would go like this. This is a logarithmic model. Which is what a lot of large businesses use, right? Like Walmart, for example, or Costco. Yeah. As the number of units approaches infinity, if you have thousands and thousands of units, the cost gets cheaper and cheaper, right? Now, you might remember from algebra that logarithms don't do that. That never happens. They don't turn down towards the x-axis. Logarithms just slowly take off to infinity, but they do it very, very, very creepily slow. Okay, so that's the idea behind a logarithmic cost model. Now let's do the analysis. Let's find the average cost to produce 1,100 units. Average cost to produce 1,100 units. No calculus here. You just take your function, plug in 1,100 for X. And don't forget there's an X in the denominator. It's the average. And then do the whole thing on your calculator. So I would start with the ln, so 1100. Then do your natural log. It's going to give you a decimal. Multiply that by 27. It's going to give you another decimal. Add the 635. It's going to give you another decimal. Divide by 1100. And you're going to get a decimal. And you're going to round that to the nearest penny. So that'll be 75 cents. That's it. That's just arithmetic. And again, we call it 75 cents, but it's dollars per pound. Or actually, not per pound, per unit. I don't know what these things are, so I'm just measuring them by units. How many of them? So on average, if I produce 1,100 of these products, right? Widget, whatever it is, then each one costs, on average, 75 cents or $0.75 to make. Now let's do the calculus. To do the calculus, you got to put the X back in. You can't do the calculus with the 1100 in there. You got to put the X back in, and then you got to take the derivative, which is the whole reason why I did these problems in this video, is so that you could see the quotient rule again. So the derivative of the top is 27 times 1 over X. Remember the rule for ln? 1 over X. Not 25, 27. I'm just going to use parentheses for times. The derivative of the 635 becomes 0, so that's gone. So that's the derivative of the top. Times the bottom, so times X. Minus the derivative of the bottom, 1, times the top, 635. Plus 27 ln of X all over the denominator squared. So that's going to be 27x over X. All right, 27, 1 over X times X. It's really just going to be 27. Minus, there's an invisible, well, it's actually not invisible, is it? Negative 1, it's not invisible, you can see it clearly, times 635, and then times 27. So that's going to be minus 635 minus 27 ln of X all over X squared. These are going to cancel. What's 27 minus 635? 27 minus 635 is negative 608 minus 27 ln of X over X squared. So this is our average marginal cost function. And now we can plug in the 1100. Oh, I might have to do a part 3 because I have used up all of our time. I'm going to finish this problem though. So what do we got? ln of 1100. 1100 ln. That's ln of 1100 times 27. All right. Technically, it's negative 27 I'm going to go ahead and put the negative in front of it. And then I'm going to subtract 605. I'm afraid I'm going to screw this up, so I'm going to write it down. Negative 794.08276, blah, 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 blah. Divided by 1100 squared. Yeah. It's less than a penny. I'm going to double check my math here, though. Let's see. 1100 squared. Yep. It is what it is. 794.08276 divided by 1,210,000. Yep. That's what it is. It's less than a penny. Again, now if this happens, this is 0. You don't have to put negative 0. So this is rounded to the nearest cent. It's way too small. I'm not going to, try to make up a different problem for this. And so if this happens, then that means that the average marginal cost to produce 1,100 of these units is 0. It's decreasing because it's negative, but it's decreasing at such a small margin that it rounds to nothing. So it's almost like it costs nothing. I am out of time. I will check my notes and see how much of this needs to be put into the next video. I have a few more examples of marginal averages. Maybe I can do a supplemental, not maybe, I will do a supplemental video for that. But until next time, I'm Dr. Jordan, and I'll see you on the internet.